Thank you very much for the introduction, and thanks again for the incredible honor. I'm a little sheepish about it, just knowing the quality of some of the other folks in the fellowship. So, I shouldn't say too much more before I say the wrong thing, but I'm really touched. So in this talk, I want to talk about some of the work I've been doing in my graduate work, and since then, in phase change heat transfer simulations that are applied for energy systems, and really what the potential is, or how can we apply simulations to improve practical energy technologies. So first, just before I actually get into the technical content, I'd like to acknowledge all the folks in CSGF. I think this photo was taken the first year I was at the fellowship, and it was, or first year at this program, and it's just an incredible crowd, a lot of friends, a lot of good colleagues here. I'd also like to thank my PhD advisor who made it out here for the talk, and I'm very honored by that. And this is the group I worked with during graduate school, and just another great crowd and people who helped me out a lot along the way. And then also, I'd like to just acknowledge the practicum here, which was a great opportunity for me to do something a little different, and I had a wonderful advisor there, Dr. Guillen. So with that, I just wanted to make sure I said that while I still had everyone's attention and before we get into the details here. So just to give a little background of what we're interested in, 40% of US primary energy goes into generating steam or vapor, either in power generation or industrial cycles. And this is all the energy coming from things like natural gas, coal, oil, nuclear, other renewable sources. And we're using about 40 exajoules a year in the US to produce steam and vapor for other processes. And then of that, a lot gets rejected back to the ambient through the process of condensation. So about 72% of that is not converted to mechanical work, it's just rejected as waste heat. And to get rid of that waste heat, we also use a lot of cooling water. So it's about 40% of our annual water withdrawals in the US. So how we do phase change is a big player in how we use energy in the States. And it's not too surprising that phase change shows up a lot, and it's really in most of these energy-intensive processes. And the reason is that if you think about kind of a comparison here, if you have a 1-liter bottle of air and you heat it up from 100 degrees to 200 degrees Celsius, you can only really store about 100 joules of energy there. But if you have that bottle of water and you boil it, you can store about 20,000 times as much energy in that process. So as a result, we see it in all these energy-intensive processes like power generation, when we're using thermal energy to produce steam and then rejecting it through condensation, and air conditioning, which is particularly relevant this week here in DC, which we're using for evaporative cooling on the inside conditioned space, and then we reject that heat to the outside through condensation, or in other industrial processes such as distillation, where we're trying to selectively evaporate and condense parts of mixtures. And all of these come into multi-phase flows where you have the conversion between the liquid and vapor phase. And these are really challenging flows to model because you've got these two distinct materials. The density ratio between the two could be 1,000. All the fluid properties are very different. You have these sharp discontinuities across the domain where it goes from liquid here to vapor inside a gas bubble. You have changing topology, so as the flow progresses, you have breakup and coalescence, and these are pretty challenging things to model. And there's also a wide range of scales here. So just looking at this little picture, this snapshot from an experiment we ran, the smallest scales of these two-phase flow features are really much different size than the largest ones. And here's just a video we took this summer of two-phase flow in this pin-fin array that's intended to break up the flow so we get lots of interface area for heat and mass transfer. And you can see that there's just all this continuous changing of topology as these bubbles break up or coalesce. So it's a challenging process to model. And we can think about this kind of in this context of the 3 pillars of science or engineering, which shows up, and I think I learned about it for the first time at one of these talks here. And what can you do with the analytic theory or the analytic models to study phase change? Well, you can look at very simple processes, and these are useful building blocks. So if you want to look at a process like boiling, you can think about a single nucleation site on a wall, and there's a bubble that grows out of there, and it's spherical, and it doesn't interact with other neighboring nucleation sites until it gets big enough that it lifts off here. And on the other side, we have experiments, and these are really useful because we can get, for sure, real answers. We can study very complex processes, like here there's a demonstration of an enhanced geometry for boiling that has these paths in there to improve fluid circulation. But the generality is kind of limited, so you can't necessarily take results from one fluid and apply them to another fluid that you might want to use in an energy system. And then on the other end, these are simulations, and I think there's great potential here, and you can get very high fidelity results. You can get things that you can't measure well in experiments, but these are still in their infancy for phase change flows. And this is just kind of a demonstration of a bubbly flow work done by a colleague, but even with very large computing resources, you might only be limited to studying relatively small problem scopes, not full reactors in a nuclear application, as in this one, at this level of resolution. So this is kind of the theme for the work I do and the motivation here, which is we want to go from understanding through simulations and experiments how these processes start at the nucleation site level in boiling or something similar in condensation, how these feed into understanding the full flow transport processes, and then how can we design thermal energy systems using insights gained at those levels. And what we tried to do in our group, and what I tried to do a little bit in my graduate work, is see how we can complement experiments and simulations together. So certainly experiments are needed to validate computational models, so you can do kind of side-by-side experiments and simulations to make sure your simulations work. But also there are ways that these can do things together that you can't get alone from either. So for example, here's a simulation of a condensing droplet on a surface, and we're getting the temperature field inside the droplet, which is something that at this scale would be really hard to measure. But also, on the other end, this is a distribution we got from a study of bubbly flow in a channel. And from this, we're able to measure in real time basically hundreds of bubbles that might take weeks or months to simulate. So there's kind of this interplay of what can you get best from simulation, and we should do it that way, or what's a lot more efficient to just do the experiment, and how can the two feed together. So with that kind of background, I'll go into the outline for the rest of the talk, which is I want to show two particular applications of how simulations and also experiments can feed into advancing energy systems. So one is for an absorption refrigeration cycle that I worked on in my graduate work, and here we're looking at flow evaporation in channels. And then a second application is dropwise condensation, which is a very efficient mode of condensation heat transfer, and I think it has some promising applications looking at desalination and water treatment. And then I just wanted to talk about a couple open research challenges for doing these sorts of phase change simulations, just to give a feel for where some of the frontiers are, or what are some of the real needs. And then I'll just conclude the talk. So just to give a little background here of what we're looking at with this refrigeration cycle. So the cooling cycles we're most familiar with require electricity or mechanical work to run a compressor or pumps or other auxiliary components. And that means that you can really only run them in applications where you have reliable electrical infrastructure. So in this project, we were looking at what would be called a single pressure absorption cycle that only takes thermal energy input, only takes heat to run. It doesn't require any electrical input. So you could use this, for example, off-grid if you needed cooling for medicines or vaccines using just solar heat. Or also if you had an application where you had a lot of waste heat, for example, from a stationary generator, and you wanted to recover some of that waste heat to run a cooling process, either for cooling a space or for cooling food or something like that. So the cycle here that we're looking at is called the diffusion absorption refrigeration cycle. And as we mentioned, it only takes thermal energy as an input. It doesn't take any mechanical work. And it operates with three working fluids, which is a refrigerant that gives you the cooling, an absorbent, which is a solvent that'll absorb the refrigerant, and then an auxiliary gas in the cycle. And an important feature is, since we don't have any mechanical input to the system, all of the flows inside have to just be driven by buoyancy or other passive means. So here's an overview of how this cycle works. We start here in a reservoir with concentrated solution, which is the solvent with a lot of refrigerant dissolved in. It flows to the stage where we add heat, and here this heat boils out a lot of the refrigerant vapor from solution. And then as the refrigerant vapor rises up due to buoyancy, it lifts some solution with it in a component called a bubble pump. So then at the top, the refrigerant vapor separates out, and we condense it to a liquid. And then this refrigerant liquid, what we do is we contact it with that other gas, which is a dry gas, and that causes evaporative cooling, a lot like sweating. And that's really where we get our cooling effect. And as these two gas and refrigerant streams stay in contact, they flow down this evaporator and they cool the refrigerator or conditioned space. And then finally, we take that wet gas mixture, bring it into contact with the solution, and basically reset the system to the initial state. So there's been a lot of work on these absorption cycles, but the ones that you can go out and purchase require very high source temperatures. So that means that they're either heated with a natural gas or propane flame or electrically heated, which means that you can't really use them well off-grid. So what we were interested in is how can we get this cycle to run using very low source temperatures in maybe the 110 to 130 degrees Celsius range that you could get from a stationary generator exhaust waste heat, or you could get from solar thermal heating. So if you look at kind of the cycles here, there's some that operate at higher temperatures and can give you higher efficiencies, and there's some that either have higher evaporator temperatures or need forced mechanical circulation, and we want to kind of operate in this window here. So to get that performance, we really need to focus on a couple of the system components. One of them that I'll talk about mostly here is that bubble pump. And just to give a quick refresh, this is the component that takes the rising vapor and uses it to circulate the working fluid and basically gets the whole system operating. And the goal is, how can we predict the flow rates of liquid and vapor through the passive system given the other operating conditions, like how much heat we're putting in, what's the size of the components, what are the fluid properties. So this is just a cartoon of the bubble pump. And basically, we're supplying the heat down here. We generate this refrigerant vapor, and it rises up through a narrow tube, and it lifts liquid through it. That gives you the pumping. It actually looks a little different here, where the rising refrigerant vapor bubbles have this bullet-shaped form. This is what kind of develops naturally in the flow, but it's the same basic idea as in the cartoon. And one of the challenges we found is that for the conditions where the bubble pumps typically operate, which is in a certain range of sizes and fluid properties, we really don't have a complete understanding. We know a lot about the flow at very large scale channels like you would find in oil refinery or oil extraction applications. And we also know a lot about at the microscale, but where these tend to operate best is kind of at an intermediate range. So to start off this project, we ran experiments for the flow. So this is a case where the experimental side is a lot more accessible and it can give us some good information. So we ran some two-phase flow experiments of the bubble pump operating at the realistic conditions, and this is a high-speed flow video from that study. And we're looking at the Taylor flow process going up through a tube. So we developed a high-speed or an image analysis code for this, so we can measure a lot of the important parameters that you can just see from the experiment. So you can see the bubble rise velocity, the volume fraction of the gas phase, the thickness of the liquid film that drains around the bubbles, and other properties along these lines. And we got some nice results. We were able to kind of bridge some of the microscale models with the models for large-scale channels in these tubes. But there's some things that you can't measure well from experiments. So while the experiments could give us the bubble rise velocity, the film thickness, and so on, it's very hard to measure the pressure fields, for example, inside this channel, so that we know what's the pressure loss in this region between the bubbles, what's the pressure gain in the film that's sliding around the bubbles, and so on. So that's really an area where CFD or simulation can come in and give us a lot of the information that's harder to measure. And I'll just give a quick overview of the simulation approach we were applying for this two-phase flow problem. And it's called the volume of fluid approach, although there are many others that people have adopted in the literature. And the basic idea is that in the flow, we have an additional field called alpha, which represents the volume fraction of the liquid in each cell on our simulation mesh. And what we can do is this field alpha gets advected with the mean flow. So as the fluid flows through the domain, it pushes along the volume fraction, so that lets us know how the interfaces are evolving over time. And also, once we know the volume fraction of liquid in any cell, we can use that to find the fluid properties like the density or viscosity or so on in a given cell in the mesh. And then we can also figure out the surface tension by performing certain operations on that phase fraction field. So here's kind of a cartoon of how this works. So let's say we have a droplet of fluid A and a volume of fluid B. Then you could represent the volume fraction or the phase fraction in each cell of the mesh, kind of here shown just by the darkness of the cells. And let's say there's some representative flow, like a shear flow, that's being applied to the droplet there. Then it would advect or push the phase fraction of the fluid into each cell like this in this distorted shape, and that would represent the bubble that had been sheared. So what we did first is we applied this just to looking at that adiabatic flow in a vertical tube. First, we did some experiments or comparison with experiments to make sure that our simulation approach was reasonable. And then we can also look at a lot of conditions that are hard to measure experimentally. So we can just continuously vary the flow rates, we continuously vary the surface tension effects, and we can see how that affects the bubbles rising through this tube. We can also just continuously vary the viscosity. So these are studies that are hard to do experimentally because the fluid properties in practice can't just be continuously changed. And the real advantage from the simulations is that we can really get a lot of local information that would be hard to measure. So here's the unit cell of this rising Taylor bubble shown on the left over here. And I've just rotated it sideways so it lines up with the graph. So the black curve here is the trace of the pressure along the unit cell. And what we can do in simulations is, because we know a lot about the flow, we can just subtract out the hydrostatic pressure or the weight of the fluid, and we can get the dynamic terms that are harder to identify experimentally. So if we subtract the weight of the fluid from the total pressure, we can get the different components of pressure drop. So this slope here tells us the pressure change gradient in the film region around the bubble. This slope here, which continues around the chart here, shows us the pressure drop in the slug of liquid between the bubbles. And then by taking the difference, we can figure out what the transition effect is between the two. And these are harder things to measure experimentally, but we just get them really readily from the simulations. So up to that point, we were just looking at the adiabatic flow, so a Taylor bubble rising in a tube. But we also need to think, how are we going to be able to operate at the low temperatures like we set out? So if you look at the conventional bubble pumps, this is kind of what they look like. On the bottom of the bubble pump tube, there's a little bulb, and all the heat is supplied right at this spot here to generate the vapor. And basically, this little pocket of vapor grows until it gets large enough to just climb into the tube and rise as a large bubble. But because all the heat is being inserted right in a small area, you don't have very much area for heat transfer. So to move a certain amount of heat, the heat transfer rate is UA, the heat transfer coefficient, times the area times the temperature difference. So if you have a small area, you need a very high temperature heat source to operate this component. So what we were interested in is, how can we reduce the source temperature? And we can do that by supplying heat along the whole length of the component. So if we do that, we have a lot more heat transfer area. We don't need as high of a temperature difference, and we can use low-grade or waste heat sources. So the challenge, though, is that in this case, all the heating happens here, and then the flow is basically adiabatic. It's just fully developed. There's a fixed flow rate of vapor. Here, the flow rate of vapor continuously increases as we boil more and more of the refrigerant out. So what we need is a good modeling or simulation approach where we can follow the developing flow along the length of the component. So to do this, we went back to the simulation approach, and now we modify it so that we can study the phase change process. So the idea is that, going back to our mesh, on each cell that happens to contain the interface, we apply some phase change source terms. So in this particular approach, we use an idea where we say that for each delta t, each time step of the simulation, we apply a source term that basically returns the cells on the interface to the saturation temperature. So this is just an equilibrium approach. We basically return to the equilibrium condition on the interface each time step. And then from there, we can get the volume generation of the liquid phase and also the amount of dilatation that goes on. So how much liquid turns into vapor and generates a large volume of vapor. So here are the governing equations for this flow, which for folks who do fluid mechanics are pretty similar to the Navier-Stokes equations. Here in the continuity equation, which just represents the transport of volume, we have a source term because you go from the low density or the high density liquid phase to the low density vapor phase. In the phase fraction equation, we're generating one phase from the other. And then in the energy equation, you have this heating source term right on the interface. So here's kind of how this works out in practice. So let's say here's an example problem. We have a bubble that's rising in a subcooled pool of liquid. So this yellow region is the bubble, and it's going upwards. And because the liquid is subcooled, the bubble will condense. And at the nose of the bubble, the rate of condensation is going to be higher because the bubble is kind of reaching fresh liquid that's not been heated yet. And at the tail, the condensation rate is going to be lower because it's already warmed up the fluid back there. So then if you apply this source term into the energy equation, you get the temperature field, which has a thin temperature boundary layer in the front, and then this wake region where the fluid's been heated up below the bubble as it's rising. So what we can do is we can take that and we can apply it to this continuously heated bubble pump design. And the configuration we're looking at is something like this on the right. So to blow it up, what you have is the middle tube here, where there's the rising two-phase flow. And around it, there's a little jacket of heating fluid that's flowing with the fluid, and that basically transfers the heat to cause the evaporation to progress. So here's just a little snapshot of a low-resolution simulation we did early on. And it's a little hard to tell from this study here, but the vapor rate, flow rate increases about 10% along the length of this component. And for a full-size device, it would increase more significantly. So some of the results we can get from these simulations are the local temperature field inside the flow, which again is something that would be challenging to measure experimentally. And what you can see here, although it's a little difficult, is in the temperature field, in the wake around the, in between the bubbles, there's a real thinning of the thermal boundary layer. And what's happening there is that liquid is flowing down around the bubbles through a thin film, and it hits this little pool of liquid in between as a jet, and that mixes up the flow. So what happens there is that there's a real enhancement of heat transfer due to this jetting and mixing effect. So if you use some of the conventional models that haven't accounted for this for flow evaporation heat transfer, they would really underpredict the rate of overall heat transfer, which is what we show up here. And this green curve is for a model that we corrected to account for this resetting of the thermal boundary layer. So this is really an application of how, by better simulating the flow, we can get some improved understanding of the heat transfer process and then better predict or better design these thermal energy components. So finally, we wanted to put this all together back into an actual refrigeration system. So shown on the right here is the experimental system we built at Georgia Tech. And this about 1.8 meter long component is the bubble pump, which is about the height of a typical refrigerator from our experience. And here's kind of a cutaway of what it looks like. So it has the boiling flow going through a middle channel, and there's a coupling fluid that's heating it that flows together with the flow through a jacket on the outside. And the idea is that that coupling fluid could come from something like a solar thermosyphon or an engine or generator coolant loop, something like that. Here's a cutaway of the evaporator where the cooling's delivered, and we have a coupling fluid loop for that, which allows us to measure the heat transfer rate to the evaporator. And then finally, this is the absorber component, which is another one we worked on that I haven't really focused too much on in this talk. So putting this all together, we were able to actually deliver refrigeration-grade cooling at source temperatures of about 110 to 130 C. The coefficients of performance, or the efficiency of the system, is not very high compared to conventional refrigerators, but the important thing to note is we're using very low-grade waste heat or very low-grade thermal sources that you might not be able to use otherwise. So we were also able to get the evaporator temperature low enough to do freezing even. So it basically means that you could use something like this for some of these off-grid emergency cooling needs. And we're able to meet our original goal of taking this technology and, by kind of redesigning some of the key components, operating it at lower source temperatures and still getting this refrigeration-grade cooling. So with that, we were kind of showing an example of how we can apply simulation and experiments to redesign some of the components in thermal energy systems and try to advance the technology to a new application. So here I'd like to talk about another work we have that's in progress, which is applying some simulation approaches to dropwise condensation with applications in water desalination. So this is an ongoing area of work that I'm starting now at Penn State. So just to give a little background, condensation, or heat transfer by turning from vapor to liquid, can go through really two modes on a surface. You can either get a continuous film that forms on a surface and it flows down and the heat's transferred through the film. Or you can also get dropwise condensation, which is pretty familiar. We see this happening, for example, on a soda can outside. If it's cooled down, you'll get lots of liquid droplets forming on it. And this dropwise condensation mode is actually very preferred because it has lots of this interface area right near the contact line. So in the film, all the heat has to go through the full thickness of the film. Here, lots of the heat can be removed right around the little periphery of each of the droplets. So as a result, you can get about 10 times higher heat transfer rates. But a real challenge is how do you avoid a dropwise condensation situation, which is desirable, turning to a film condensation rate where you have much lower heat transfer rates. And a challenge is that as these droplets form and grow, they can merge together and basically form a film. So somehow you have to remove the droplets fast enough to keep the process going. So here's basically a little theory of what happens during dropwise condensation. So you have a surface that's being cooled, and there are all these little imperfections in the surface that act as nucleation sites for droplets. And you can get areas up to maybe 10 to the 9th droplets per square millimeter, so very high density of these sites. And basically droplets form in each of these sites, they grow and they merge with other droplets, and they just get larger through that process. But once the droplets get large enough, they can actually slide off the surface because gravity is pulling them down or some other mechanism removes them. So what happens is if you have a droplet here that got large enough to slide off the surface, it wipes clean the whole area below it and gives all this area for the process to reinitialize. And as it reinitializes, you get these smaller droplets that have much higher heat transfer rates than the large droplets. So as long as you can keep this process going where you slide off the large droplets, wipe clean the surface to keep it restarting, you can get effective high heat transfer rates. And an important thing to note is that you might think of the individual small droplets as just rigid spheres or parts of spheres, but the important thing that causes the process to reinitialize is the sliding of the large droplets. So there's an interplay between the small scale, where a lot of the heat transfer happens, and the large scale, where the dynamics drive the process. So here's an application of where you would use dropwise condensation, or where it's been recommended. So there's a process called vapor compression desalination. And what you have here is a tank of brine solution, or seawater. And over the liquid layer, there's basically vapor steam or vapor water. So what happens in this process is a compressor extracts some of this steam, compresses it to slightly higher pressure, and then sends it through this recuperative heat exchanger. And in that heat exchanger, the steam goes through, and seawater flows down on the outside. And basically, there's a heat transfer. So the condensing steam going through heats up this seawater flowing on the outside, and it generates more steam that's then sent back through the process. And then finally, the warm condensed water coming out is used, and we can recover a little heat from it to preheat that saltwater stream coming in. And then we can also recover some heat from the pool of brine at the bottom. So it's a recuperative process, and it can be very efficient. But an important process, or important component here, is this recuperative evaporator condenser. So we want that to run as efficiently as possible so that we can keep the whole system going effectively. And some recent publication argued that if you can get this component to operate in the dropwise condensation mode, you can significantly reduce the capital cost because you can use a smaller compressor, and you can also reduce the thermal resistance between the two sides. So somehow we want to keep this condensation process going here in the dropwise mode without transitioning to film. So again, we need some good understanding of how the dropwise condensation progresses so that we can predict the change between the two modes. OK, so here's some representative questions that come up when we're trying to understand this dropwise condensation, and some questions that I think we can answer well with simulation if we have the right approaches. So one is, how can we just predict the heat transfer rate in the first place from this process of dropwise condensation? What's the effect of the large droplets? So we know the small ones are basically rigid spheres, and they don't really move much, but the larger ones can have dynamics. They can slide, they can merge, they can do some pretty complicated things. And then, for example, by better understanding this, can we engineer film removal paths? So we can tailor a surface maybe to better remove the film so that it keeps restarting rather than just starting with a blank surface. And there have been a number of numerical studies of dropwise condensation, but what all of these have done is they just take the nucleation sites and they model them as rigid hemispherical droplets that grow until they bump into each other, but they don't really capture the fluid mechanics, which is something we want to get at here in this study. So here's the idea that we want to apply to this problem, and we want to use a multiscale approach. So the idea is that the large droplets have important hydrodynamics, so those we want to resolve in this VOF approach. But in between them, there are these numerous small droplets that we might be able to model in a subgrid scale approach. So in between these larger droplets, we have these small droplets, and we can maybe just take the average effect because there's so many of them, we can't necessarily resolve each one. So to start with, let's look at how we can capture the effects for the large droplets. So an important challenge here with the larger droplets is that a lot of the heat transfer happens really close to the contact line where the droplet meets the wall. And there's actually a subcontinuum heat transfer resistance. That's a pretty important effect, which is called the interfacial thermal resistance. So what we can do here is we can put in a closure model to predict the heat transfer rate due to this interfacial resistance. So what we have here is there's a temperature difference over the resistance, and it's also multiplied by the area, which has a delta function centered on the interface. So that might be how you would express this sort of in the analytic sense, but it's kind of challenging to apply this delta function on a mesh or in a finite volume way. So the approach we use is, let's say here's the droplet shown in the finite or in the volume of fluid approach. And if you zoom in on the interface, you have the interface that's spread out over a few cells where it goes from the vapor side into the liquid side. So what you can show is that there's this area times the delta function centered on the interface can be represented as a spread out or smeared delta function over a few cells as the gradient of this phase fraction times the volume of the cells. So this is just an approach of taking a problem that happens on the interface and making it so that we can apply it over a few cells of a mesh so that we can kind of keep consistent in our same approach of using this finite volume solver. So to start with, we did some validation studies for this approach. So here's showing a droplet growing on a condensing surface. And as the droplet grows, the temperature distribution inside the droplet evolves over time. And what we can do is we can compare the growth rate of the droplet predicted with this numerical approach to that predicted with an analytical approach that's actually a pretty classical one. And we were able to show that we get pretty good agreement over the course of the droplet growth. So we can accurately predict the heat transfer rate for a single droplet. So now that we can accurately predict the heat transfer rate for a single droplet, we can start looking at some new things that weren't really tractable with some of the earlier numerical approaches. So one here is looking at what happens when these droplets coalesce. So some of the earlier approaches would just say that the two droplets, they grow and grow until they bump into each other, and then now they're a bigger droplet. But the intermediate stage is actually important because as the droplets come together, they can flow, they can have some internal circulation. So here's a simulation. Let's see if this comes up. There you go. Of these two droplets that are getting close to each other, they merge, and then the overall droplet that's larger has some oscillations until it kind of stabilizes out. And this is for 100 micron droplets initially. So going back into this simulation, we can extract some information that would have been possible to get with the earlier approaches. So one is, what's the heat transfer rate during this droplet merging process? So this red line here is the heat transfer rate that would be predicted for the two droplets kind of sitting side by side. They have more interface area. The green line is what you'd expect if the two droplets had kind of stabilized out at the larger size, merged together. So it has less interface area, so that number would be lower. But the blue curve is the simulated heat transfer rate, and it's actually higher than either of those curves, and that's because the droplets, as they merge, have lots of mixing going on. Another interesting result is the surface area that's covered by the two droplets on the wall. And this kind of oscillates over time as the two droplets come together. They kind of go back and forth. And what that might imply is that the amount of small droplets that are picked up by the large ones would be different than if you just said that you have two droplets and now they're a bigger droplet, because when the droplet gets squeezed, it might catch more of the small droplets and reinitialize more surface area. So what we can now do is take this approach and apply it to a larger domain. So rather than just starting with two droplets, we can look at many and start to get a feel for the overall process. So this is only considering the grid scale heat transfer. We don't account for the smaller droplets in between, but we can start to see how the process evolves when you have many droplets that are starting to get packed together on a surface. So now we need to think about what happens for the really small droplets that you couldn't resolve on that mesh. And we're trying to still develop this subgrid scale approach, but a basic idea is this. If you think about the area between the large droplets on a surface, over time, there should be small droplets that are generated there and they grow larger and larger. So what we can say is that the heat transfer rate on the subgrid scale, or the heat transfer rate between the large droplets, decays over time, and it depends on some kind of effective age, since a part of a surface was last cleared from the large droplets. So if you track that over time, you can get some of these curves which were developed in an earlier study. So the idea is that we can take these curves for the small droplets and plug them into the spaces between the large droplets to accurately predict the overall heat transfer rate. So this is still a work in progress, but I just wanted to show you a representative snapshot from one of the studies here. So on the left is the grid scale droplets, and what you see is almost no heat transfer except in the thin contact line regions around each of the droplets on the wall. So this is the wall, and these are kind of the hot spots on the wall. And in between those large droplets, you have the subgrid scale heat transfer, which represents the billions of tiny, tiny droplets that have most of the heat transfer. And the hot spots here, these red streaks, are basically where droplets have coalesced and kind of wiped clean, fresh surface area to allow the process to start over again. So this is just kind of showing how we can couple those grid scale fluid mechanics with the subgrid scale modeling of basically the rigid droplets to get a better picture of the overall process. So in these two sections, we talked first about an application in refrigeration cycle and studying the flow evaporation of these Taylor bubbles going through this bubble pump. In the second application, we talked about dropwise condensation and potentially how it could be applied to important problems like desalination. So here I just wanted to talk about a couple open research challenges that I've come across or seen in this field of phase change simulation, and just kind of get a feel of where these go. So first thing that I kind of touched on in the Dropwise talk is that you have this huge range of scales. So in Dropwise condensation, you could have as many as 10 to the 9th droplets per square millimeter. So if you think about a 5 centimeter square of surface area and you want to simulate it, and for each droplet you just want to store its position, x, y, and also its size or radius, and you want to store these three quantities as floating point doubles for each droplet, then you might need 55 terabytes of memory. That's big. We do have computers that have that much memory, but in practice you might even need more than that because this is a very optimistic estimate. Similarly, in boiling, you go from micrometer scale nucleation sites on a wall where vapor bubbles form up to centimeter scale flow structures of vapor and liquid slugs. So to model boiling, you also need to kind of capture this wide range of scales. And I think there's this possibility that really hasn't been exploited a whole lot for multiscale models. So can we capture the hydrodynamics with the large scale models, the really small scales with the subgrid modeling, and can we do the same thing for boiling, going from nucleation sites to small dispersed bubbles in the liquid flow to the larger bubbles and liquid structures in the channel. So another application here is thinking about what happens when these interfaces come together and you get bubbles that either coalesce or droplets coalescing and breaking up. So most of the solvers, including the one I was kind of showing here, predict this coalescence process or breakup as basically when the interface thickness becomes less than one cell in the mesh, then you basically have two bubbles coming together or two droplets coming together. In practice, what happens when you get to those really small scales is a little bit more challenging. I just want to show this video from an experiment we ran this summer that kind of shows what happens in practice. So we have a channel flow. There's a layer of liquid on the bottom, and we're bubbling gas up from underneath. And I want to kind of just direct your attention to this part of the video here. So there's this vapor bubble, and it'll recycle in a second, that forms and goes up, but it doesn't actually merge with the gas layer on top. It bounces off a few times. So if you want to model some of these processes, you have to think about what's happening in the really thin region right between where that bubble came up and where it hits the liquid layer. So that's an open challenge. And one argument that was made recently was that you really can't even model this on the continuum scale. You need to go to the subcontinuum scale to capture what's happening during these merging and breakup processes because your interface is eventually going to the scale of individual molecules. So with that, I'd like to just briefly give a summary of some of this work and an outlook for kind of future directions for these phase change simulations and energy systems. So the approach we talked about here is applying these phase change simulations at the phenomena scale, looking at individual Taylor bubbles or droplets, taking insights gained there and looking at full flow boiling or dropwise condensation processes, and then ultimately trying to apply these to energy systems, whether it's this refrigeration cycle on the left or, for example, a desalination system on the right, and trying to take advances from these smaller scales to apply to the full energy systems. Another thing I'd like to highlight is just the potential for complementary simulations and experiments. So yes, you need experiments to validate simulations, but there's also other potential ways that these two can contribute together. And finally, there still are some open research challenges in studying these two-phase flows, certainly many. And one is just thinking about this huge range of scales from the largest processes that have important dynamics to the really complex microscale. And then also what happens when you get to the limits of these continuum mechanics and you just need new approaches to capture these thinning interfaces. So with that, again, I'd like to thank, and I'm deeply grateful to my advisor, Dr. Garamella at Georgia Tech, for all of his advice during this work. And also Krell and CSGF, who've been an incredible community and supporters and made a lot of this work possible. And also a number of the colleagues I've worked with along the way to try to develop some of these techniques and methods. So with that, I'd like to thank you all and happy to answer any questions.